my hands are mirror images, but they're not superimposable. So if I only had, say, right-handed gloves, well then my left hands, they're kind of out of luck. And the same thing is true about the molecules in our body. The whole idea of molecules having like the same chemical makeup, even all these same linkages, but different orientations in space, is called stereochemistry. So we can call these different versions stereoisomers. And when we have versions that are these non-superimposable mirror images, we call these enantiomers. And the way that they can form is because they have these different like chiral centers where the molecules can attach in different ways in 3D space. If you were to look inside of your cells or inside of the cells of like any organism, you'll typically only find like one version of each molecule. So it's like you only had right hands. And correspondingly, all of like the enzymes, so like the proteins in the cells that are formed to like make those, bind those molecules and use like burn together molecules and make bonds between them to form new molecules, those are all stereospecific too. Like you only have right-handed molecules and you only have right-handed gloves. And so if you tried to put left hands into there, well, that's not going to work. And this can be a problem for the pharmaceutical companies when they're trying to like make a drug, and the way that traditional like organic synthesis works, you end up getting a mixture of these products. So you get this like racemic mixture, so you have like equal amounts usually of like both hands. And so sometimes this isn't really a problem, such as with like ibuprofen. If you have both versions, it's okay. Your body can like interconvert between them, and it's not that big of a deal because the other one's not harmful or anything. But for drugs like thalidomide, the two versions, like one of the versions has like these sedative effects, and the other version can form like these birth defects. And so it can be this real problem. And so in a lot of cases like that, like your body can interconvert between them, so you can't even just like separate them out and then be okay. But for some things, your body can't interconvert or that sort of thing, or even if it could, it's less efficient and whatever. So you want to be able to introduce stereopure compounds. So there's only a single enantiomer. So for like synthetic chemists, this can mean that you have to do a ton of purification of each product at each point. And then you're like losing half of it at every step. So your yield's going down. So they need methods to be able to catalyze these reactions. So to speed up these reactions, in a way that is stereospecific or asymmetric. So you're not getting equal amounts of both, you're getting mostly one of the products. And so traditionally, ways that have been doing this were with either like metal-based catalysts or with enzymes. And so enzymes are what our bodies use. So they're biological catalysts. And they're typically like proteins or protein and RNA mixtures. And so they're these big complexes, and they're really well suited to perform specific reactions in a specific way in your cellular conditions. And so if you were to try to put these enzymes into the conditions that are normally used in like organic synthesis, which are really harsh conditions, those enzymes wouldn't be happy. So we can use enzymes for synthesis, but we typically have to then chemists have to then like alter everything to suit the enzyme's needs, and then you have to potentially purify these enzymes along the way and express and purify these enzymes. So this is this whole big problem, and then so basically this isn't ideal. And the metals aren't ideal either, because that's not very environmentally friendly, and the metals are picky too, so they don't like oxygen or moisture, so you have to do them under these like highly controlled conditions. And so metals aren't great. Enzymes aren't great. Well, enzymes are really great, but like in our bodies, they're harder if you're trying to synthesize like reactions that don't normally happen. So that's another thing with enzymes, is because you can't just, I mean, people are working to try to design enzymes to catalyze specific reactions that they don't normally do, which is really cool. But they're really well suited. They've evolved to do specific reactions very specifically. So it's harder to control, like being able to get them to do things that they wouldn't normally want to do. And so with like synthetic chemistry, you're wanting to often make molecules that have like never been made before. So you need to be able to more tightly control everything. So you need to use those harsh conditions and do various things with various substrates. So the substrates are things that like the catalyst will combine or somehow modify to make the product. And so basically we need another solution, organocatalysis. And so this was what the winners of this year's 2021, well, yeah, this year's chemistry Nobel Prize, David Millen and Benjamin List, for organocatalysis. And so what is organocatalysis? So So I want to tell you more about this and how it's really revolutionized the field of like synthetic chemistry because it's really opened up this third route. So you have the metal catalyzed, the enzyme catalyzed, and now you have this organocatalysis. And what's really great about it is it can be more environmentally friendly, and you can also do like cascade reactions. So when reactions happen in our body, it's typically like a chain reaction of different enzymes. Like, so this one, it's like does one step and then another step and then another step and then another step. When you do things in synthetic chemistry, it's typically like do one step, purify that intermediate, do another step, purify the intermediate, do another step, purify the intermediate, and using like different reaction conditions for each. And so with cascade synthesis, the idea is that you can kind of make a chain reaction happen without having to purify along the way. And if you can do it in this enantioselective way, so you're getting just like this, just the right hands or just the left hands, then you don't have to worry about like purifying it out every intermediate in order to try to like reduce the amount of unwanted byproducts. So yeah, so I've been really geeking out about this. I want to tell you more about it. So, organocatalysis. What the heck does that mean? So, organo means that we're talking about like an organic molecule. Okay, well, what do we mean by that? When we talk about organic molecules, typically we're talking about something based on a carbon-hydrogen backbone. So you'll often hear it just being like carbon-based molecules, but sometimes there are a few weird instances of carbon molecules that have carbon, but we don't consider them organic. So typically organic molecules are based on this carbon-hydrogen backbone. And carbon's really awesome because it can form like 4 different bonds to other molecules. So it's very versatile, and it's kind of flaw in its reactivity most of the time, and especially if you put it with like hydrogen. So you can form these carbon hydrogen backbones that can really serve as like a sort of skeleton for then having different functional groups. And so functional groups are things like carbonyl groups, which is a carbon double bonded to a hydrogen. And so if you have this on the end, we call it an aldehyde. So if it's just like attached to a hydrogen here, or in the middle, it's like a ketone. These terms are going to come up a lot more. So you can have these different functional groups and different arrangements of these carbon attached to these various things. And so that makes it really useful. So that's what the organo part refers to. So these catalysts we're going to use are based on like carbon hydrogen based compounds. Okay. Well, what is a catalyst? A catalyst is something that speeds up a reaction without being used up in the process. And so catalysis is really fundamental because even reactions that are like energetically favorable, so the products are like happier than the reactants, even those reactions will recur like really, really slowly unless you give them some help. And so the common way that our bodies do this is using enzymes. So enzymes are, as I mentioned, are typically like proteins, sometimes protein RNA mixtures. And what they do is they can kind of like hold the substrate, so things are going to react like in the enzyme in an environment in a way that it will be favor the reaction occurring. So it can do this. I talked about enzymes a lot before, but it can do this in ways by like holding that, like just bringing them together, because you have all these things floating around, and it can kind of help keep them like right next to each other, as well as kind of like pull on various like electron clouds and stuff to try to get the charge regions in a way that favors them binding. And sorry, that's not very helpful, but I don't really want to talk about enzymes that much today. I want to talk about how we can get away from using enzymes in these organic synthesis routes. So one of the reasons why enzymes are so important for in this whole talk is because they have such specific stereoselectivity. And that's because these enzymes are these big proteins and stuff that have this, their active site where the reaction like actually happens is itself like a 3D form, and it has all these amino acids. So protein letters are called amino acids, and the way that it's situated, like it's perfectly like all of the chemistry and stuff is right there, so it binds to these reactants and stuff in the ideal way for the reaction to occur in a specific way. And so this specificity goes down to the level of the stereochemistry. So let's back up and talk about stereochemistry a little more. Okay, I have a test for you. Are these the same? How about these? It turns out that these are actually the same. If I were to rotate them, they would actually be the same. But these aren't. These are enantiomers. They're they're non-superimposable mirror images. So like my hands that I talked about before. So this idea of stereochemistry comes up a lot in organic chemistry and biochemistry, and we even have ways to represent it. And so we can use these representations to simplify things. We also have different ways to refer to these things. So we call them like R and S and L and D and plus and minus, and there's all these different ways. But the basic thing you need to know is that these are all different stereoisomers, and that they arise because you have like carbon centers, so these chiral carbons that can bind to different things. And so if you have a carbon bound to 4 different things, you can end up getting different stereoisomers. And if you have, so it turns out that for molecules, they often have like more than one chiral center, so you can have more than one isomer. There's a lot of isomers that aren't enantiomers. And so we call diastereomers, where they're just like different, but like enantiomers, they're non-superimposable mirror images. And that's, so that's like your right, left hand, and that's what's like easiest to talk in terms of. So that's what I will. And so the idea, the example I gave before is like thalidomide. So you can see that there's these 2 different versions of thalidomide. This S and this R, and there's also for ibuprofen, you have like S and R. And so you can see that your stereochemistry just differs at this one linkage point. But these molecules thus have different 3D shapes, and then they do different things. Acids are the like protein letters. They have this generic backbone, these unique side chains. And the way that these unique side chains can stick off, you can get like L or D stereoisomers. But in our body, we just use the L. And so you can see that this alpha carbon, so that's the one that's attached to like the side chain, and then the carbonyl carbon, and then the amine, it's a chiral center. It's attached to 4 different things. And so you can get different stereoisomers. So the L and the D. And so you can see that here with alanine, you can have this, it stick either way. So this is just showing you the 2 different
things for these mirror images that if you flip them, you can see that this group is a different arrangement. Okay, the only one that doesn't have a different, that's not, that the L and D are the same is glycine, because it just has a hydrogen, so it's the same either way. Okay, but anyway, so now we know what stereoisomer, this like stereoisomer thing is. And so how do the enzyme, how does this form? Well, a main way is that like when reactions happen, they typically reaction happens with like an intermediate where you have a like a non-chiral intermediate that it can then react to form either product depending on how the reaction proceeds. And so typically often these reactions, what's happening is you have a molecule that has a pair of electrons that's going to attack a molecule that is like deficient in electrons to form a bond. And so depending on which side they attack from, the reaction can happen in different ways and you can get different stereoisomers. So that's a big oversimplification, and there's a bunch of different reaction types, but this is just to show, like, you can imagine like if you have a molecule and you get attacked from this side or attacked from this side, you can have different things, you can get different products. And so one of the things is, well, what if you could like block attack from one side? Then it could only attack from this side. And this is one of the strategies that like enzymes use. They have, if they like hide one side, they're making it favorable for attack for the other side. And this is one of the strategies for catalysis as well. So if you can introduce or like organocatalysis or just other synthetic routes as well. So if you can use something bulky to kind of block one of the sides, you can influence where that attack's going to come from, and therefore where the stereochemistry of the final product. So let's look at how they did this. So there are really these two main like breakthrough type papers in 2000 by the two Nobel laureates. So we have David McMillan has this Iminium ion catalysis. And then we had Benjamin List with this enamine catalysis. So let's start with List. He actually got his inspiration from looking at enzymes themselves. And so although the enzyme is like this big complex, it turns out that the actual catalysis part is just happening in a specific site in the enzyme called the active site. And within that active site, it's really only a couple of amino acids that are really doing most of the work. Let me see if I can find that quick example. So take like a serine protease. So it's like a protein cutter or whatever. It really, like the whole enzyme, it has this big thing, but then within this active site, you really only have like a few amino acids contributing. And so you can see that they're kind of helping arrange things and make the electrons flow in the way that flows go. And so, yeah, so typically in like organic chemistry and stuff, we draw these like electron pushing arrows where you see like where the direction of the electrons go, because really it's like all of bond formation and breaking involves like the sharing and unsharing of pairs of electrons, as I've talked about in past posts. So sorry, I'm kind of like not going into as much background as I normally do, but I figured that I'm going to really geek out on this one. So I'm going to probably, people that don't have a chemistry background probably won't be interested enough, but if you are, I have other past posts you can refer to if you're getting confused, and sorry. Okay, so going back, so there's really only these few amino acids that are contributing. And in some reactions, there's really only just like one. And so Benjamin List have been working on trying to like simplify kind of the reactions that can occur. And so he created these like previously he worked with these catalytic antibodies. So basically he made antibodies, so little proteins raised against like that can bind to specific things. And so he made antibodies against like the intermediate for an aldolase reaction. And so an aldolase is something that catalyzes this aldol reaction, which is where you have like you have a aldehyde, so something with an OH next to the H, and then you have like a ketone or another aldehyde, and they combine to form an aldol, which has a carbon double bonded to an oxygen, so like an next to an OH, so like an alcohol. So it's like a combination of an alcohol and an aldol, and an aldehyde or whatever. So you get this aldol. And what's really valuable about these type of reactions is that you're forming a new carbon-carbon bond. And these carbon-carbon bonds are really, really valuable because remember, organic chemistry is based on these carbon-hydrogen backbones. And the part of what makes those backbones really great is they're kind of blah. But the fact that they're kind of blah makes them hard to form because they're not really reactive. And so being able to form these scaffolds is super important. And so aldol formation is a really, really critical reaction if you want to build up molecules. So they wanted a way to speed this up. And so the enzymes that normally do this are called aldolases. And so he started by creating these like antibodies that could catalyze this reaction. So basically they bound the intermediate and then they helped catalyze it like on the surface of this antibody. So he kind of shown that you can do this reaction outside of an actual enzyme having to help with the help of amino acids, with the help of like protein letters. But then he was wondering, well, can you just do it with a single protein letter on its own? So we actually used a different letter than the letter that was used in the experiment, in the actual aldolase enzyme. What he used was proline. And so we got on this idea. It had been used like in an older article and nothing really came of that. But so proline is this weirdo. And I say that lovingly. It, unlike the other amino acids, its side chain actually wraps back upon itself. And what this does is, so in structural biology and stuff, it matters a lot because it kind of locks the protein into shape because it can't rotate and stuff as much as the others. What matters here is that it's this secondary amine. And so it has a nitrogen attached to 2 carbons. We call that a secondary amine. And this allows it to serve this critical function in these reactions. And so I'm not going to try to go into too much detail because I don't want to mess up because this isn't really my super strong point, but basically, so that this is the like proposed synthetic route. So you have this ketone and this aldehyde, and then this is the catalyst. So this is L-proline. So this is the form of proline that our bodies normally use. And so you have this chiral catalyst. So you're starting with this chiral molecule that's going to help promote the specific stereoisomer product. And it actually forms this intermediate where the catalyst is stuck to one of the substrates. And so it's just an intermediate. So the idea with the catalyst is it gets used over and it can get used over and over without getting used up itself. So it's going to be regenerated at the end of the reaction. But by sticking this chiral molecule onto the substrate, now you're influencing how that substrate is going to react and influencing it towards the enantiomer that's promoted by the chirality of that catalyst. So basically you have this nitrogen. So this oxygen is pulling electron density away from this carbon. This nitrogen has a pair of electrons, so it can attack there. And then you get this like rearrangement, lose of water. Now you have this, you can have this intermediate where the electrons kind of flow to here. I'm just totally oversimplifying this. But then you introduce the RHO, so that this thing. So R is just representing like the, in this case, this part, and it's basically R can be a bunch of other different things. It's just like the rest of the molecule kind of. And what it can do is, because you now have these electrons, with this, like when you have a double bond to electrons, they can act as like a nucleophile. So they're going to now attack this carbonyl carbon, this aldehyde carbonyl carbon. And then you get more rearrangements. You have this compound stuck to your catalyst, can hydrolyze. So the water can actually like help break off the catalyst part from the rest of your molecule. And voila, you now have an aldol. So you have the aldehyde, you have the carbonyl carbon next to the alcohol. You form this new carbon-carbon bond. And so remember, R is just standing for like all of the rest of this. And what was really crucial is that they found that they had this large enantiomeric excess. So for example, with this, they had 96% of one enantiomer over the other. And so this was a really fundamental like proof of concept type of thing. And what was really cool too is that at the same time, you had a second group, so David McMillan's group, showing that you could use a different organocatalyst to do a different type of organocatalysis. So in this case, it was and I cannot say this word. Iminium ion catalysis. So List was inspired by like those enzymes, and McMillan was really inspired by metal-based catalysts. And so metals are often even used by enzymes, like enzymes as part of their like the active site, like enzymes often like hold on to metals. And when you have like organic molecules binding to metals, it's typically through like a coordination complex. So metals have these big dispersed electron clouds. And so they can really like give and take electrons pretty easily without being too perturbed by it. So this makes them really useful, because remember, the flow of electrons like between different atoms and the joining is important for like making and breaking bonds. And so enzymes can kind of give and take electrons to make those reactions happen more easily, and stabilize intermediates and that sort of thing. So enzymes or metals are really useful. And part of the reason they're useful is they can act as Lewis acids. And so a Lewis acid is an electron pair acceptor. And so a Lewis acid can act as a catalyst, and it's what they're calling like LUMO activation. So it's the lowest unoccupied molecular orbital. Basically, you just need to know that it's making it easier for that, for the site to be attacked. So it's lowering the barrier for attack. And so he found that you could actually use organic catalysts to do something similar. So in this case, he's using this this catalyst to form this iminium ion that is then more susceptible to attack by dying. So it's like what he was doing was this like Diels-Alder reaction. It takes an aldehyde. So remember, an aldehyde was something that had a double bonded carbon next to a hydrogen, and a diene. So it's something that has these two double bonded carbons. And it does this like cyclization reaction. So you start with something like this and something like this, and end up with something like this. And so not going into the details, but it involves the formation of this iminium ion intermediate from this catalyst. And so once again, you have the catalyst kind of serving as a scaffold that's actually binding to the reactants. And because your catalyst is once again chiral, it is directing which way the reaction will go stereochemically. And so in this article, they even show that, so you can see they have this big enantiomeric excess. So they're having like, in some cases, they have like 90-ish% of one versus the other. And you can see that, so here they're showing in like the structure that the reason why this is happening is you have these like bulky groups that are blocking one of the faces of it for attack. And so then you're mostly going to get attacked from the other side. And because, but the reaction is being catalyzed, so that like bulkiness is steric hindrance. So steric hindrance is something we use to refer to basically the idea that two things can't be in the same place at the same time. So they'll clash. And so the bulkiness can like prevent the clash. And then you also have this catalysis, so this like speeding up because of that iminium ion formation, where you're having this like pull of electrons because of that positively charged nitrogen, and that's lowering the barrier for attack by that aldehyde, and allowing you to get the product formation. So if you want to, and a key thing, a really cool thing about organocatalysis is that it's now being so since 2000, they've been finding like a ton of different organocatalysts and different reactions that they can catalyze. And what's really exciting is combining it with other like forms of catalysis, such as photocatalysis, so using light, as well as making like cascade reactions. So you have kind of like how in our bodies we have those like chains of enzymes working to make molecules, like one makes one product and then it passes it off to another, which does the next step, which passes it off to another, does the next step. And with organocatalysis, you can kind of do these chain reactions in a test tube. And I think I talked a little bit about that before, so I'm not going to get into it here. If you want more background, so the Nobel Prize website has some good information, but I just want to, and I'll put links, but I want to warn you that they are perpetuating this myth. This is not true. So there's this myth that lemons and oranges smell different because of different stereoisomers of limonene, I don't know. But basically the myth is that the S-limonene gives you lemon and the R gives you orange, and this is a myth. So check out this video for more. But basically, the truth is that both lemons and oranges both have almost like 95-ish% of the R isoform and very little of the S. And that's not the reason why they smell different. The reason why they smell different is because of they have a bunch of other different chemicals. And so don't be fooled by that myth. No, that's wrong. But you can find more information. They have like a more technical background, as well as the more like generic audience backbone. background. Yeah, so sorry that was kind of weird and rambly and a little outside of my comfort zone. But I'm trying to get more into my comfort zone with organic chemistry again. And I just thought this all was really exciting. And so I hope that that wasn't just super confusing. If it was super confusing, I'm sorry, and you probably left by now. But if you're still here, I'm sorry. So yeah, so hope you found that fun too.